is called finding the volume using the integrable known cross-section. That sounds exciting. We're going to find the volume using cross-section. So we're going to be looking at a solid that has, no matter how you slice it vertically, like in any way, and you open it up, you're going to look at a certain cross-sectional area that will be the same no matter where you go. You'll have circles, going all the way across it. It sounds weird, but it's going to start to make sense when we start drawing pictures. Or maybe you slice it and no matter how you open it up, it looks like a square, or it might look like an equilateral triangle. And we might have, as we go through, the first, if we slice it right at the end of the solid, this geometric solid, we might have like a really small little, that's supposed to be an equilateral triangle. And then right next to that, there's a slightly bigger equilateral triangle. And then right next to that, there's a slightly bigger one, and then a slightly bigger one. And you put all of these things together, and it looks like some solid. Right? So we're going to think about an easy case to start with. Think about a cylinder. Okay? I'm going to take a cylinder, and here's my cylinder, right? And if I take my cylinder and I slice it vertically, right, straight down the middle, and open it up, what do I get? Right, I'm looking at the face of the circle, right? Exactly, that's what it looks like, right? You take any cylinder, take this toilet paper here. Got the toilet paper in case I got to throw it at the wall. Slice it right through the middle. Can you people in the Zoom see that? Slice it right through the middle. Oh, and there. Now you're joining the Zoom too. I open it up, it's a circle, right? Good? Okay. Take a lacrosse ball. I happen to have one up here from yesterday. Perfect. Slice it straight through the middle, open it up. What do you get? Circles. Slice it right at the end vertically. Open it up. What do the cross sections look like? Circles, right? Smaller circles than if I slice it through the middle, but still circles, right? Doesn't matter where I slice it, it becomes a circle. Okay? This is how most things are. Here we go. There we go. Tissue box, right? Slice my tissue box. Tissue box. Ooh, tissue box. Slice my tissue box vertically here. What do I get when I open it up? I get rectangles. Right? No matter what, they're always rectangles. Okay. Take don't need Zoom, I'm just moving furniture, don't worry. Take a bag of wooden objects. Got a bag of wooden objects. Okay. What's this one? It's a cone. You guys see the cone at home?
Yes.
Yeah, okay. Take my cone. Let's say I have my cone. Can you guys see it at home? Can you guys see it? Yeah, in the cabinet. If I take my cone and I slice it and I open it up, what do I get? Circles, right? Doesn't matter if it's oriented this way and slice it horizontally. Still open it up. What do you get? Circles. Okay, perfect. Good. Cones. Here's my tissue box again. We don't need to do the tissue box again. Here's my pyramid. Here's the pyramid. Here's another pyramid. That's what I wanted to do. All right. Triangular pyramid, right? Yeah. It's just oriented. Let's say it's standing on its base like that. Slice it this way. No matter where I slice it along the entire height of it, as long as it's perfectly horizontally, open it up. What do you get? You get a triangle. Square pyramid, same thing, right? Slice it. What do you get? Open it up anywhere. You get a. Yeah. Okay. These are the basic. These are all basic geometric solids. These ones are easy to know what they look like. Right? They're easy to think about. Get a weird looking one. Okay. This one, somebody 3D printed this one for me. Ooh, fancy. See that 3D printing thing? Ooh. You guys all see it? Ooh. Fancy, huh? Okay. So the base of this one it's not perfect, but it's supposed to be a parabola, but cool 3D printers and video, right? It's supposed to be a parabola here, right? So the base of this thing, you guys see that? Ooh, it's supposed to be like a parabola. You guys see that? Can you see it? You guys can see it at home?
Yep.
Yeah, okay. So the base is this parabola. Base is the parabola, and you'll note that if I were to slice this thing, what do the cross sections look like? If I slice it anywhere along here, the cross sections look like triangles, and we get some sort of weird looking shape here. And what we're going to be dealing with is objects that look like this, and you can see, like those of you here, you can see that there's like, I'll show you to the Zoom people in a second. Those of you here, you can see like that there's like a bunch of these little triangles going through that it's out printed. So we're going to be thinking about this like it was, there's an infinite number of these little triangles. They're very, very thin, right? So you guys see how there's all these like little ridges here? There's all the little triangles. Like each one of these is like a little triangle. Can you guys see that?
Yeah.
You can see that, yeah. You guys can see that? Okay, so we're pretending like we have an infinite number of these little triangles to create these weird looking solid objects. This is what we're going to be dealing with. Things like this. Things like this. Yeah? Okay. So that when we slice them horizontally or vertically, there is a cross section that we know every single one of these is a triangle. This one happens to be, I don't know, it's supposed to be, I think these are supposed to be equilateral triangles. So each one is an equilateral triangle. We should be able to write a formula to represent the area of any cross section. Then we're going to use an integral to sum together all of those little areas to get a volume. Does that conceptually make sense? And think about, we'll take an easy case again, like a sphere. Right? Think about a sphere. Right? I could slice this into an infinite number of little very, 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 very thin circles. Right? And each of those very, 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 very thin circles you can find the area of. And then they each have a very, 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 very small thickness to them. And so if we multiply that area by that very, 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 very small thickness, we get a very, 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 very tiny volume for each of these little like discs that we get. And we'd sum them all together, and then we'd have the full volume. Conceptually good? Conceptually good at home?
Good.
The theory is we're going to do that with any shape we want. Right? Take my square prism here, slice it into an infinite number of very, 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 very thin squares that have this tiny thickness to them, find each of their volumes, sum them together, get the full volume. Everyone good there? That's the concept. That's what we're doing today, and really what we're doing tomorrow and Monday too. Okay. Cool. That's what all this crap up on the board says. Yeah? It says find the volume by slicing. So we're going to sketch our solid, sketch this cross section of it, find a volume, or find a formula for the area of it. Then we're going to figure out, how long this thing is. Those are going to be our limits of integration. And then we're just going to integrate all those area formulas to find the volume. That's all it is. Conceptually good? Wonderful. Conceptually good at home?
Yeah.
It's so good that I'm in the classroom because I haven't had this. I didn't have this for quarter 3 people. The people here are looking at me like I'm nuts. I don't know, Zoom people. People probably think I'm nuts too. All right. So what we're going to start with is a solid where the base is the curve y equals 2 root sine x. Seems like a stupid thing to have the base be, right? But that's what it is. Right? Make it something weird. I don't know. Maybe we want to make like a weird paperweight. I want a paperweight that has the base look like 2 root sine x, right? So I can feel like I know how to do math while I'm holding my papers down. And we've got cross sections that are squares. So no matter how I slice this solid, when I open it up, I'm going to get a square. I might get a really small square, I might get a bigger square. Okay? But we're going to slice it and get squares. And we want to find the volume of this solid. So first thing we need to do is sketch a picture of this. Okay? So what we're going to do is we're going to sketch what 2 root sine x looks like. You guys know what 2 root sine x looks like? No? Hopefully vaguely, right? You know what sine x looks like, right? It looks basically like sine x, except that we don't get any of the negative values. And it's, it's the square root, so it doesn't quite look exactly the same, but it looks fairly similar. And if it's got a 2 in front, it's going to go up to a height of 2. So really, 2 root sine x from 0 to pi just literally looks like this. Okay. That's not perfect. It's probably like a little bit steeper, but it doesn't matter for this purpose. We're just drawing a picture. So we're going to say that no matter how I slice this, I've got this object coming if you're in the classroom, out of the board right at you. And if you're at home, it's just coming right out of the screen at you, right? And it's squares coming out at you. So I'm going to try. My drawing skills are garbage. So I'm going to try to draw this. So like I have, if I were to look at it like this, here is a square. That was worse than usual. A square sticking straight out of the board at you. And closer to the end, the squares are a little bit smaller and then a little bit smaller. And the further up we go, we have larger squares. And think about there being an infinite number of these squares that start out really tiny on both ends and slowly get bigger as you would slice it. And so it's coming out of the board at you with all these squares. Does that sort of make sense? Those of you that are here? Okay. Those of you at home, does that sort of make sense what you're looking at?
Yeah.
Yeah, it's hard to conceptualize. Just think of it like, all right, this is the thing that we're looking at here. And so my base is, I had a parabola, right? So my base was the parabola here. Well, coming straight out of that parabola, coming straight up are these triangles, right? So I get something weird looking like this. Well, this is going to look something weird also, except that instead of triangles, I'm going to get squares. And if anybody's in engineering, 3D print me one with squares. Because the person that made this only had time for one before the pandemic last year. So anybody in engineering want to print me one with squares? Yeah? No? Cool. All right. Conceptually, okay though? Squares? Right. Squares are easy to find the area of, aren't they? What's the area of a square? Yeah, based on, and then they should be the same, right? Since they're squares, so it should just be whatever one of the side lengths is, squared, right? The area of our square should just be the side length squared. Now, each of the side lengths of these squares are different, are they not? Right? Some of them are small, some of them are large. Y'all agree with that at home?
Yeah.
Cool. Way to not answer. Okay. So the side lengths are all different. So we are just going to use a generic formula for the side length as our area, which we'll find in a second. Now, as we slice these things, they have a very, very small thickness to them, right? They can't see me. They can't see me pointing at the board at home, can they? Oh well, they'll survive. They have a very, very small thickness to them. And in what direction is that thickness? It's going left to right, isn't it? A very, very thin, sounds weird. A very, very thin thickness in the left-right direction. And the left-right direction on a coordinate plane is the x direction. So the thickness of these is in the x direction. Now, think back to when we originally, way back, and we didn't review this because we're going to talk about it today, way back when we first started talking about integrals a long time ago, and we did all these Riemann sums. What did we do? We took a bunch of rectangles, didn't we? And we added together rectangles, and we said, well, if we had like 8 rectangles under our curve, that'd give us an okay area. But if we had 100 rectangles, it'd give us a better area, right? And if we had 1 billion rectangles, we'd have a really, really, really good approximation for the area. And we made those rectangles very, very, very thin, just like we're making these squares very, very, very thin. And what did we call the thickness of those rectangles when we were finding the area? dx, exactly. We called those, the thickness of the rectangles dx. And that's what we're going to call these. These have a very, very, very tiny thickness in the x direction. We're going to call this dx. We call it dx because it's infinitesimally small. Right? It's an infinitesimally small change in x. That's what dx represents. If we were slicing it horizontally, it would be an infinitesimally small thickness in the y direction, and we'd have dy, and we'd have to do it in terms of y. Does that make sense at home and here?
Yes.
Got an answer to that. Okay. All right. So as soon as we figure out that we have a very, very small thickness in the x direction, that it's dx, we then know that everything else in this problem has to be done in terms of x. Okay? So if I knew that it was sliced this way, horizontally, to give me squares, I'd have to do everything in terms of y. But the problem says the cross section perpendicular square, the space is running from the x-axis to curve. Usually it says perpendicular, but I wrote running from the x-axis to the curve. So my cross sections are going this way, right? They're going in the y direction, so the thickness is in the x direction. Everybody's good? I'm not going too fast or too slow. We're okay. Okay. At home, you're good?
Yeah.
Okay. So this right here is the side length of one of our squares, right? How could we write an equation for that, or write a formula for s in terms of x? What is s equal? Because I would love to do this, right? I would love to say, all right, let's integrate from 0 to pi. That's the length of this, right? Those are what my limits of integration should be, 0 to pi. I'd love to integrate s squared dx. But I can't integrate s squared dx, right? Because those variables don't match up. S squared has to be written in terms of x, right? So how do I write s in terms of x? S is just the distance from the x-axis to the function. True? Well, that's actually a distance in which direction? The y direction. In fact, it happens to be y, doesn't it? I mean, whatever this point is, it's some point x, comma, y. Whatever this point is, it's some point x, comma, y. Right? It's whatever y. Well, what does y equal? Y equals 2 root sine x. So I can replace s with y with 2 root sine x, and then I should be able to integrate. So we're going to say an integral from 0 to pi of 2 root sine x squared dx. And we square it because it's s squared. Because that's the formula for the area of the square. Everybody here good with that or no? Any questions on that? Because if that one didn't make sense, the next ones aren't going to make sense either. So I want to make sure you're good. Everyone's good. People at home, are you good?
Yeah.
You want to see
Yeah.
that? What do you want to see? That's supposed to be a problem. Reading printing. 1 second, people at home. Zoom. Not supposed to. Good. All right. All right, everyone's good? So all we're going to do then is this integral. Well, what's 2 root sine x squared? Or sine x, right? So this just becomes, I'm going to work from right to left now, apparently. This just becomes an integral from 0 to pi of 4 sine x dx. And what's the integral of 4 sine x?
For negative cosine x.
Negative 4 cosine x. Good job at home. Negative 4 cosine x. And where do we need to evaluate this from? 0 to pi. So this becomes negative 4 cosine pi minus negative 4 cosine 0. Cosine of pi is negative 1. So negative 4 times negative 1 is positive 4. And then minus the negative is plus. Cosine of 0 is 1, so 4 times that is 4. We get 4 plus 4. We get 8. And yeah, units cubed. That's fine. You don't need to write units cubed. Question? Well, not for this one because it says it's squared. I mean, this one, this is not representative of every shape. This is just representative of one specific one that some student made for. So yeah, they're all going to have different cross sections. I could say that they're cross sections that are, regular pentagons or something, which would be a complete pain, but I could do that. And then you'd have to know the formula for the area of a pentagon and find that and sum them together. Does that make sense? Yeah. Okay, cool. At home, are you guys good or no?
Yeah.
Is that a yeah or a nah?
I
Yeah.
have a question.
Yeah, question.
Where did the S, like, I get where S came from, but where did the square came from?
Where did the squared on the S?
Yeah.
Because we are looking for the area of each of these squares that we've got here. And we've got these squares here that are the cross sections. And so the area of that square is the side length squared.
Okay, thank you.
Does that make sense? Yeah. Cool. Anybody else at home questions? Everybody here is good? Okay. All right. Let's see if we can do this whole next problem right here. I doubt it. Okay, I'm just going to draw the picture here. So we've got the same curve, y equals 2 root sine x, but now our cross sections are equilateral triangles rather than being squares. Okay, so not much is going to change about this. I mean, we're going to redraw the picture here. Here's 2 root sine x. And instead of having cross sections that are squares, now each cross section is going to be an equilateral triangle. And so this one, Ryan, would look, it would look more like this, right? More like this. So we got equilateral triangles running across here. And the length of one of these, we'll just call it the side length there. The side length is still 2 root sine x, isn't it? It's just the length from the x-axis to the curve. So that's helpful. The thickness is still in the x direction. So this thickness should still be dx. So the only thing we've got to do is figure out what the area of an equilateral triangle is. And you should, I hope, know the formula for the area of an equilateral triangle. No, that'd be for an isosceles right triangle. You might not know the formula for the area of an equilateral triangle. You can use some right triangle trig to figure it out, but I'm going to tell you that you should memorize this because it'll make your life easier in general. The area of the equilateral triangle is s squared, the side length squared, times root 3 divided by 4. You should know that formula for the area of an equilateral triangle. Okay. If you don't know it, just memorize that. It's easy. S squared root 3 over 4. You can use right triangle trig to figure it out, but that's not, I don't think, a good use of our time at the moment. So just know that formula. Good? Okay. So as we put together our integral for this, we're going to need to integrate from where to where? 0 to pi, because they're the same limits as the first one. Good. And it should be the side length squared times root 3 over 4. Well, what's the side length? 2 root sine x, right? So 2 root sine x squared times root 3 divided by 4 dx. So all of this first part before the dx is just the formula to represent the area. That's side squared root 3 divided by 4. The dx is the thickness of each of those equilateral triangles, so that when we multiply the area of the triangle by the thickness, that gives us a tiny little volume. And then we integrate, we sum together all those volumes from 0 to pi. Conceptually good still? Okay. At home, conceptually okay?
Yeah.
Wonderful. Okay. Let's simplify our integral. Let's integrate and let's evaluate. Should be easy, right? So the 2 squared is 4, which is going to cancel with the 4 in the denominator. I'm going to have a root 3 still though. We can always take a root 3 outside if we have a constant, or we can always pull it outside the integral if we want to. So we have root 3 times the integral from 0 to pi, and then we have root sine x squared. Well, what's root sine x squared? Sine x. So we just have root 3 times the integral of sine x dx from 0 to pi, and we just did the integral of sine x a minute ago. It's negative cosine x. We got root 3, we got negative cosine x. We got 0 to pi, and negative cosine pi minus negative cosine 0. Like we said before, cosine of pi is -1, the opposite is 1. Cosine of 0 is 1. The opposite of that is still 1. So we end up with 2 inside of here. Yeah, if it's a constant, you can pull a constant in or out, however you want. Yep. Anytime you want. As long as it's a constant. Nothing with a variable. Nope. Our root 3 is in the numerator. No, we're just pulling it straight up. We're not adding anything. I mean, normally I would have to add something in, then we multiply by the reciprocal outside. Oh, yeah. But we're not adding anything in. We're just saying, all right. I could have left the root 3 in there. It wouldn't matter. They would just been root 3 sine x, and the integral would be negative root 3 cosine x. But you can also pull it. Good? Yeah. Okay. Good. Everybody good here? Okay. Everybody good at home? Any questions at home?
Nope.
We're feeling okay or no?
Yes.
Okay. It's always like the same 3 people that say things, so hopefully the other.
Wait,
Oh, okay, I'm
So-
waiting.
what does the numbers mean, or the answer that we get?
What do you mean?
What exactly is that? Is that the area of the triangle, or?
No, that's the volume. That's our volume. I just put this. This is just the formula you need to know for the area of the cross section. Then the 2 root 3 is the volume. So the original question was here: what if the cross sections are equilateral triangles? Right? We're looking for what is the volume. So that's the volume. 2 root 3 is the volume of this geometric solid that we've created. Good or no?
Is it the same solid? Are we still finding the same solid, the volume of the same solid?
We've done 2 different ones. We did one with the cross sections of the squares. That was the first one that came out to be 8. And then we did the second one with the equilateral triangles, the picture down in the bottom left here. Over here. This one. And then I just finished, and we finished that on the second page because we ran out of room. Good or no? Are you good or no?
Yes, I think.
All right. Let's take a look at another one and see how it goes. If you have issues, let me know. All right. This one's going to be a little more difficult. I'll give you guys a second to read it, and then maybe you guys can try to draw your picture. Maybe try and draw the picture on your own, and then we'll work through it together. Make sure your picture looks good. And I'll just take this cone that I have and stab the toilet paper on it. Perfect. I don't think they can do that at home. Maybe they can. I don't know. Can they do the toilet paper stabbed on the cone? You guys are missing out. The toilet paper on the cone. All right, try to draw your picture. You guys at home draw a picture?
Yes.
Yeah? How about here? You guys got a picture drawn? Still working, some of you, yeah? Give me another minute here to draw your picture. I'll go over here and make my key. That's the first day. First day. Exciting. All right, here is one arc of the curve 2 sine x. Looks very similar to 2 root sine x, doesn't it? Yeah. Our integral is going to be a little bit more of a pain this time. Having the square root there was nice because we had to like square things and then the square root went away. But now we don't have that. We're going to have a sine squared. That's going to be a pain. So here's the base of our solid. And then coming out of the screen at you or out of the board at you here, we have cross sections that are, if we cut perpendicular to the x-axis, so if we cut this vertically, the cross sections when we open up look like semicircles. So, semicircle, 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 semicircle. Bunch of semicircles sticking out of the board at you. Okay? Some of them are very, very small over here in the corners, and they get bigger towards the middle, and then they get smaller towards the end again. Right? Conceptually, okay? How many of these semicircles do we have? Please don't say 5. How many do we have? An infinite number of these semicircles, right? And we're going to find the area of the face of the semicircle, multiply it by a thickness of dx, right? The thickness is going to be dx because they're very, very, very thin in the x direction. So this is going to be a dx problem. Now, what is the area of a semicircle? Pi r squared over 2. 1/2 pi r squared. All right. Can I integrate from 0 to, where are we going to? Looks like it's pi again, right? Pi is where this will hit the x-axis. So can we do 0 to pi of pi r squared over 2 dx? Can I integrate pi r squared over 2 dx? No, I have to turn, let's see, the pi is fine because that's a constant. The over 2 is fine because that's a constant. But the r squared has to be turned into terms of x. The same as our d, whatever, dx, right? So we got to turn r into terms of x. So how do we do that? What is the radius of this semicircle in terms of x?
Half of 2 sine x.
Not quite 2 sine x.
It's y.
So our diameter of the semicircle, right? This is the diameter, right? Our diameter is the height of the function, right? So we're going to say over here that the diameter should be 2 sine x, which tells us that the radius should be just sine x, should be half of it. Everybody good with that? Everybody here good with that? Everybody at home good with that?
When I heard semicircle, I thought it was different. I don't know. It's weird for me to visualize the y-axis is a straight line. Like I thought the semicircle would continue down to the x-axis. How would I know that it doesn't do that?
The semicircle does go down to the x-axis.
I was visualizing it like it's a.
What?
I don't.
Say it again.
I was visualizing it like it was a half, like the whole figure was like a half a sphere.
No. I'm not sure how it would be half of this. here. I guess I'm not understanding exactly what you are thinking it is.
Mr. Bachelor,
Yes?
this is kind of, I think this is kind of related, but how do you know which way the semicircles are oriented?
Okay, so we know that they're oriented in the direction that they are because it says that if we cut it perpendicular to the x-axis, we get semicircles. So if I had drawn my semicircles like this and I cut it perpendicular to the x-axis, I don't get a semicircle, right? I only get a semicircle if I drew them the way that I have them up there when I cut perpendicular to the x-axis.
Okay, thank you. That's what I was missing, and thank you, Ian.
Everybody's good there at home now, or questions at home?
I mean, does it matter if when you do the semicircle, does it matter if it looks like the letter D, like how you drew it out, or if it's like inverted?
And then you drew them facing this way?
Yeah, like would that make a
No,
difference?
that's fine. No matter. Won't change anything.
Okay.
Just so long as you didn't draw them this way. Because then that's not perpendicular to the x-axis. Good?
Yeah.
Any other questions, Zoom? Okay, everyone here is good still? All right. So our radius is sine x, so we just plug our radius in up here. So this becomes an integral from 0 to pi. Let's see, the pi over 2, like we said before, is just a constant. So if I want to, I can pull that out to the front. So my radius, which is just sine x, is squared, so sine squared x. Everybody good there? Now the question is, how do we integrate sine squared x? Now we did this way back a long time ago. Yeah. It is unfortunately not either of those. We have to use a trig rule to rewrite it before we can integrate it. Not the product rule. What? No, like a regular trig rule, like from before this class, to rewrite it sine squared. You cannot integrate sine squared as is. Well, okay, that's sort of a lie. In Calc 1, you cannot integrate sine squared without rewriting it. That's right. It's a power reducing formula. So, do you all remember what the power reducing formula is for sine squared? It's on the required trig identities that you need to know paper that's in the other documents folder of the Google Drive. Should be in there. What is sine squared x equal? Is this something you should know? What is sine squared? Exactly. It's 1/2 of 1 minus cosine 2x. You should know that. You should also know the formula to reduce cosine squared. It's 1/2 of 1 plus cosine 2x. But the only one we need right now is the sine squared. Okay. So we will replace sine squared with 1/2 of 1 minus cosine 2x and rewrite this integral as pi over 2 times the integral from 0 to pi, 1/2 of 1 minus cosine 2x dx. Everybody good there? All right. Now, once again, I've got a 1/2 out there in the middle of my integral. I can take that constant and pull it out. So if I pull the 1/2 out, the constant in front of my full integral is now going to become pi over 4. And in order to integrate the cosine 2x part of this, I'm going to have to use a in reverse. When we use the chain rule in reverse for integration, we call it a u substitution. Right? We're going to have to use a u substitution to integrate cosine 2x. But I don't need one to integrate to 1. So normally, if you've got part of your integral that doesn't need a u substitution and part of your integral that does. If you can't just do the u substitution in your head, which it would be good if you can do the u substitution in your head, because you're going to want to be able to do that eventually. If you can't do it in your head, separate it into two different integrals. Okay? So we're going to pull the 1/2 out to make it a pi over 4. An integral from 0 to pi of 1. That's the first part of the integral. Minus the integral from 0 to pi of cosine 2x dx. And remember that pi over 4 is being multiplied by the whole thing. And so integrating 1 should be pretty straightforward. If you integrate 1, what do you get? X. So this should become pi over 4 times x from 0 to pi minus, and then now we're going to have to do our u substitution. So how we're going to u sub on cosine 2x. U is going to need to be 2x. du is going to be 2 dx. So we'll put in a 2 and a 1/2 to cancel each other out. And this becomes minus 1/2, and I'm going to make sure that pi over 4 still gets applied to everything. Minus 1/2 of the integral, and it's no longer going to be 0 to pi. What's it going to become? It's going to become 2 times 0, still 0. And it's not going to be pi, it's going to be 2 times pi. We're going to use that. And now it's an integral of cosine u du. Everybody good there? Any questions here in the classroom? Yeah. I had the cosine 2x from before, right? Already. So I just flip that. And then I just, in order to get my du of 2 dx, I needed to put a 2 in. So I put the 2 in, I put the 1 out. Good? Okay. At home, are you guys good?
Yeah.
Okay. Anybody at home have questions? Got questions? Okay. And everybody here is okay? Yeah? Okay. Cool. All right. So now we'll just finish doing all the stuff here. We got pi over 4 times. We got pi minus 0. Okay. Minus 1/2 of, well, what's the integral of cosine u? Sine u. And we're evaluating that from 0 to 2 pi. So we have pi over 4 times pi minus 0 is pi minus 1/2 of sine of 2 pi minus sine of 0. Well, what's the sine of 2 pi? 0. What's the sine of 0? 0. So I've got pi minus 1/2 of 0. Well, 1/2 of 0 is 0. And so I got pi minus 0, which is just pi. So all of this just becomes a pi inside of 0. I have pi over 4 times pi, or pi squared over 4. Good or no? Everybody here good? Sophie, all right? You're like, it's a lot of work. It's a lot of work. Yeah, yeah. A lot of fun. A lot of fun. At home, are you guys okay?
Yeah.
Yeah? Nobody at home has any questions? Everybody feels okay about that? Everybody here feels okay about that? All right, what do we got? We got 24 minutes left. We're doing okay. We're gonna go. Yeah, question. Sure. All right, here's the next one we're gonna look at. That's right. Now we got this one and one more. We may only have time for a few of the limits multiple choice questions today, and then we'll do the derivatives ones tomorrow. Tomorrow. This is a quick longer than I thought. Here. All right, read the question. Everybody in the classroom is reading the question, but those of you at home, I can't tell if you're reading the question. So read the question. This one's a fun one. See if you can draw your picture. We didn't start yet. They're just drawing the picture and reading. Oh, that's Andrew that's supposed to be there. But Andrew's at home today. Oh, I'm going to Zoom.
They said that I wasn't supposed to be in there in the first place. It's kind of funny.
They said you weren't supposed to be here in the first place?
Yeah, like they said my my paperwork didn't come through or whatever, like the form I submitted. They said that like I didn't submit it in time or something. So I wasn't supposed to be.
That's that you're on my roster.
Yeah, no, but I wasn't on like Levine's, and then they checked my like status on Power School, and they're like, "Oh, you're not supposed to be here." And I was like, "All right, guess not."
All right, well, all right. Guess you're home now until you decide to come back. I think there's probably going to be space because it doesn't seem like that many people really want to be here. I got 4 people showing up for my second period. Yeah, 4 people in second period. And the class is mostly seniors. I guess that's probably why, but. All right, we got a picture or no? Y'all got a picture? You got a picture? Akash, you got a picture? Yeah? Leopold, you got a picture? Okay. Austin, right? Okay. Yeah? Okay. You got a picture? I should be able to remember. A for Austin. U of A for Austin. Yeah. There we go. Y'all got pictures, right? Okay. You got home? You guys got a picture drawn? Cool. Good response. Okay. Here is our circle. X squared plus y squared equals 1, or less than 1 out of 51. So it's this disk, right? This circle here. Okay. This is the base of our solid. The cross sections, which are perpendicular to the y-axis, so it's different this time. Cross sections are perpendicular to the y-axis. Okay. Are isosceles right triangle with one leg in the disk. So if you have an isosceles right triangle, the 2 sides that have to be the same, right? Because it's isosceles, have to be the 2 legs. Okay. So here is an isosceles right triangle. Here is another isosceles right triangle. Here is another isosceles right triangle. And so on. A bunch of isosceles right triangles going through there. Okay. What is the area of an isosceles right triangle? What's the area of any triangle?
1/2 base times height.
1/2 base times height. Good job, Zoom. Okay, 1/2 base times height. Well, if these are isosceles, what can you tell me about the base and the height? should be the same, right? So it should be 1/2, just the length of one of those squared. True? Base and height are the same. It's called length squared. So this is L, length, right? Generically, for whatever triangle I'm looking at, that length is L. Okay. And we need to do this in terms of which variable now? Y. And why do we have to do it in terms of Y? Why do we have to do it in terms of Y? None of you think that I'm funny. It's fine. I don't care. All right. We have to do it in terms of Y because, well, our cross sections are perpendicular to the y-axis, and so these little triangles here have a thickness in the y direction. They have a thickness of dy. So what we want to integrate is from y equals -1 from the bottom, right? From y equals -1 to the top, which is y equals 1. And you don't have to write the y equals. You normally wouldn't have to write that. I'm just writing that to make a point that we're doing this one in terms of y, not in terms of x. So if you were on the AP test, you don't have to write y equals. So we're going from y equals -1 to y equals 1. 1/2. I can put the 1/2 out front, right? No problem there. 1/2 out front. Length squared dy. But L squared dy is not something I can integrate because the variables don't match up. So we got to figure out what L is in terms of y. Well, there's a small problem with that because in which direction does L stretch? L stretches in the x direction. So first, let's write L in terms of x. And then we can convert it into terms of y afterwards. So we're going to try and write L in terms of x. Question? What do you mean they stretch through the x-axis? L is in the x direction because it's perpendicular to the y. That's why it's going. At home, any questions? Any questions?
No.
Okay. Everybody here is good still? Okay. All right. So we're going to write L in terms of x. All right. So L in terms of x. Well, how do I measure? How'd you get 2x? Is it you? You did. How'd you get 2x? Right. So from the y-axis to any point on the function should be x units, shouldn't it? I just go over x. Well, if these are going across a circle is symmetric, this should be the same distance to the right as it is to the left to reach the circle. True? If our circle is centered at the origin, which it is, based on the equation we have. So this is x, which makes the whole length there 2x. So what is L squared? Should be 4x squared. Do you all agree with that? Okay. So I could replace L squared with 4x squared. Not good enough yet, but it's a start. So we've got now, let's see, if I put a 4 inside of here, I can pull that 4 out and multiply that by the half, which would make it a 2. So we'll put a 2 out in front. Now I'm still going to write y equals -1 to y equals 1. You don't need to do that, but I'm going to. What I have inside of here now is an x squared dy, right? Which is still not okay. It's better because L is just some arbitrary crap that we've thrown in there, some variable we've made up. At least x is like related to y in some way, right? How is x related to y? Well, like this. X squared plus y squared equals 1, isn't it? Based on the equation we were given. So if x squared plus y squared equals 1, what does x squared equal? 1 minus y squared. Everybody at home good with that?
Yeah.
Okay. Everyone here is good with that? You guys are more responsive than they are in the Zoom, so I feel like you guys are good, okay? Yeah, okay. So all we have to do is replace the x squared in our integral with 1 minus y squared, and we're good. Right? So now we've got 2 times the integral from -1 to 1 of 1 minus y squared dy. We can integrate 1 minus y squared easily enough, right? What does that integration become? Integral of 1 is y, and the integral of y squared is y cubed over 3. So we have y minus y cubed over 3 from -1 to 1 gives us 2. And the first part here, we got 1 minus a third. We plug in 1. And then minus, plug in -1, we get -1 plus a third. 1 minus a third is 2/3. -1 plus a third is -2/3. Right? So we got a negative -2/3 there. So we got 2/3 plus 2/3 is 4/3 times the 2 should give us 8/3. Good? Are you guys good with that at home?
Yeah.
Yeah.
All right. Everybody here in the classroom is good? Anybody have any questions? Home, Zoom, questions? No questions. Okay. I think we're going to stop with that one with our new step for today. And then I'm going to take the last, we got 10 minutes or so, and I'll start doing questions from the limits multiple choice. Tomorrow, we'll start with questions from the limits multiple choice and the derivatives multiple choice, and then finish that up before we do any more new material. The quiz that we're going to take on Friday will solely be on what we did today. It will just be on what we did today. Everybody at home hear that? The quiz on Friday is only on what we just did right now. Not just this problem, but the problems we did today. Good?
Good.
Okay. Yes. Just what we did today. Just what we did today. Yeah. Yeah. I don't know. We'll see. Nah, nothing like that horrible. The cross sections will be relatively normal. Semicircles are like a quarter circle or a triangle or a square or a rectangle or something. And you will find in Google Classroom, there is a document that I posted this morning before school called called volume by cross section. And there is a document there with practice problems. And there is my worked out answers and solutions to it also. So I'd like you guys to work on that tonight so that we can answer questions on that tomorrow also. And that's what we're going to do for today with the new stuff. So now I have my book where all of those multiple choice questions on limits and derivatives came from. So we got about 10 minutes here. We're going to do any questions that you guys might have from the limits packet there. Because remember I sent the reminder and was like, do those questions. And so you all did them because I didn't ask you to do anything else. Right? Or you'd already done them before. So whether you're Zoom or here, you can just tell me what you have questions on. If you're in Zoom and it's easier for you, you can just type them in the chat. If you're here, you can just shout them out. 37! That's a good one to start with, I guess. I don't know what it is. So let me flip through the book and find 37. 37. Oh, yeah, that's a good one. All right, number 37. Y'all are looking at your limits multiple choice stuff at home?
Yep.
All right. Zero, the limit of x approaches 0 of the square root of 3 plus the inverse tangent of, what is it, just an x? 1 over. Okay. This one's a little bit of a tricky one, and because it seems like if you plug in 0, right, you end up with the inverse tangent of infinity. And you might make a mistake immediately there and say, oh, the inverse tangent of infinity. Well, I don't know. That seems infinite. This seems like it shouldn't exist. Right? That's the first thing you might do. That's a mistake. Because the inverse tangent of infinity is actually pi over 2. Right? Because if you think about the graph of tangent goes towards infinity at a vertical asymptote of pi over 2. And goes down to negative infinity at negative pi. That's the first thing that might throw you off, is you might just be like, oh, infinity doesn't exist, infinity. So that's not good. Okay. The second thing that might throw you off is you might have said, okay, cool, the inverse tangent of infinity is pi over 2, so the answer is square root of 3 plus pi over 2. But the problem with that is, and this is a really tricky one, this is probably more difficult than what you'll see on any multiple choice on the AP test. But if you look at the limit as x approaches 0 from the right, I'm just going to call this f of x so I don't have to keep writing it. Okay. If I look for that limit as x approaches 0 from the right, this infinity is a positive infinity, and I get the inverse tangent of positive infinity, which is pi over 2, and I get the square root of 3 plus pi over 2, which is great. Okay. But if I look at the limit as x approaches 0 from the left of this function, now we think about the inverse tangent of, well, if we're approaching 0 from the left, that's a negative number, right? So this 1 over very, very, very small number is a very, very small negative number, which makes this the inverse tangent of negative infinity. And the inverse tangent of negative infinity, as we were just looking at with our graph here, is negative pi over 2. So this would become the square root of 3 minus pi over 2. And there you'd say, oh, well, the limit from the right and the limit from the left are not the same. And therefore, this limit should not exist, which is choice E. That makes sense, right? That's tricky. Yeah. That's tricky. I would be exceptionally surprised if there was one that difficult on the AP test. And especially if it was on the multiple choice. Maybe on the free response, where they might ask you like to look for from the right and from the left. They would probably specify you need to look at both rather than hope that you do it on your own. Yeah. So if you plugged it in and got 0 as your final thing, you're saying? I'm not sure what you mean. Yeah, I mean, generally, if it's something weird, yeah. If it's something not weird, if it's just some normal function that doesn't have weird things going on with it, then you're probably fine. Somebody said something in the chat. Let me see what this is. Could I do 9 and 10? Yeah, we could do 9 and 10. All right, everybody is good with what we just did? Here, everyone's good? Zoom, everyone's good with the one we just did? All right. Number 9 is the limit as x approaches infinity of 2 to the negative x over 2 to the x. And what's 10? Same except its limit as x approaches negative infinity. Right, so looking at these two, if we were to plug in infinity, right, we know that 2 to the infinity is very, very large, and then this becomes 2 to the negative infinity. Well, a negative power drops to the denominator, doesn't it? Right? So this one should become 1 over 2 to the infinity for the 2 to the x that's already in the denominator. And then 2 to the negative infinity in the numerator should drop down and become another 2 to the infinity. Well, 2 to the infinity is huge, and 2 to the infinity is also huge. And a huge number times a huge number is another huge number, right? So really, this is effectively 1 over infinity. And what does that become? 0. So number 9 should be 0. Good with that one? David? I think it was David that asked that, right? Yeah? Good with that, David?
Yeah.
Okay. And then similarly with this second one, right, as we plug in negative infinity, we have a negative x already in the numerator. So the negative of negative infinity becomes a 2 to the infinity in the numerator. And then the denominator is a 2 to the negative infinity when I plug the negative infinity in. So that will rise up to be in the numerator. We have 2 to the infinity times 2 to the infinity, which is a huge number, infinity. And I don't know if the multiple choice answer is it might be infinity or it might be doesn't exist, one or the other. I don't know what they wrote in that. Looks like they wrote infinity. So. Does that make sense?
Yeah.
Cool. Other limit questions? Oh, I got another chat. Oh boy. Way to keep an eye on that. Number 7. Just for those of you at home, just to remind you, everybody that's here in the classroom can see what you say in the chat. So if you think you're just sending it to me, you're not, because they're all going to see it. But number 7. Number 7 is the limit as x approaches negative infinity. 5x cubed plus 27 over 20x squared plus 10x plus 9. So for this one, we need to, first we could plug in the negative infinity and we'd see that this is becoming a very, very large number. This is infinite and this is also infinite. So if we wanted to be really thorough about this, we could use L'Hopital's rule and take the derivative and then take the derivative and then take the derivative and just keep doing that until we ended up with something that wasn't infinity over infinity. But we also might be able to just realize that the degree of the numerator is larger than the degree of the denominator. And if that happens, that means that the numerator is going to dominate the denominator and that the numerator is going to be what's more powerful. And so we'll end up with, in the end, this numerator going towards infinity with the denominator just going to some constant, eventually, something smaller. And if my numerator goes to infinity more quickly than my denominator does, it's going to infinity. Okay? And then we got to think about whether it's positive or negative. So if I plug in a negative infinity and cube it, negative infinity cubed should still be negative, right? But a negative infinity squared should be
Positive.
Infinity, right? So this is going to end up giving us a negative infinity in the long run. Now, we could take derivatives and see this. We'd get 15x squared, and then we'd get 40x plus 10, and we'd still see infinity over infinity. So we take another derivative, and we get 30x over 40, and that's where we'd see that this is a negative infinity over 40, which is negative infinity. Does that make sense? Everyone here good? At home good?
Yeah.
All right, cool. We will do more of these multiple choice first thing tomorrow, plus the derivatives multiple choice. Work on the homework assignment that I posted. If you have questions in Zoom or here, you're welcome to stay and ask. Otherwise, have a wonderful day.